To understand thermal stresses, we will take an example of two blocks over here. If you see in the figure, we have two blocks made up of structural steel and copper alloy. The copper alloy is generating heat whose capacity is 0.05 watt per millimeter cube. Because the heat is always generated inside a volume, it is not on an area. Okay, so the heat generated inside the copper block is 0.05 watt per millimeter cube. Except the copper faces in the front and back, there is convection on all the steel faces. Okay, on all the steel faces there is a convection whose film coefficient is 50 watts per meter square Kelvin, and the ambient temperature outside is 20 kelvins. Okay, the dimensions of the model are given over here, so we will be able to generate the model and solve it using the thermal stresses analysis system. Okay, so let us see how to solve this. We will come to Ansys Workbench and we will add one steady state thermal analysis. Once the system is added, the first thing that I need to do over here is I need to add one copper alloy over here. So I will add that copper alloy so that we have both the materials ready. After this, we will enter into the geometry. The dimensions are given into millimeters, so we can set the unit system as millimeters. Okay, now we will start creating the geometry. So as per the diagram, you have 60 by 60 and this is 30. So we will come over here. I'll take a rectangle and now we will create the dimensions. This has to be 60 units and this has to be 30 units. I'll give the constraints and add a symmetry. Okay. After that, come back to the modeling area and now use the extrude option to add material. But here I will say that it has to be in the symmetric manner and we will generate. So this is the first block that we draw. Similarly, I will again click on XY plane, but this time I have to say that it has a new sketch and we will enter into the sketch tool and I need to create the copper block. We will give the dimensions. This has to be 30 units and this has to be 15 units. We will use the constraints, a symmetry constraint and one more symmetry constraint for this. Come back to modeling, extrude option. Now this time again I will say it is both symmetric, but here instead of adding material I will say slice material, so that the material is cut over here and another block is created. Okay, so we have two blocks now. I will rename them. This is the steel and this is copper. Okay, so we have the two blocks. You can switch off the frozen body so that you can see the blocks. Now if you wish, you can also create 1/4 of the section because it is a symmetric model. Okay, so we can also generate 1/4 of the design and we can calculate the results. Once the geometry is ready, we can exit from the design modeler and now we will enter into the mechanical window. After you come to the mechanical window, the first thing that we'll have to do is we'll have to change the materials. So you can see that the geometry is ready. I will click on geometry over here. So for the steel block, I need to have structural steel, and for the copper, I need to apply copper alloy. So the geometry has been updated. Now let us mesh the model. So this is the default meshing that we've got. In connections, we will have one contact region, and I can have it as a bonded contact. Okay. Now, after this, we will now apply the boundary conditions. So, as per the problem description, you can see that the heat generated inside the copper block is 0.05 watt per millimeter cube. So, heat generated is this option, internal heat generation. Select the volume. Please understand, internal heat generated can only be applied on volume. You can see all the other selection toolbars have become gray. That means you cannot select them. It can only be applied on the entire volume. Give the value 0.05. Then we also have to apply convection. So here they have said the convection is on all the surfaces except the copper front and back. So I will select all my faces over here. Okay, and the film coefficient over here, they have given it in meter square kelvins. Okay, so I need to change the unit system to Kelvin first, and the unit system also I will change to meters. And now let us enter this 50 and 20. Can you see this? Okay. Once that is done, now you can add the temperature, whatever results you want to understand for thermal analysis. Once that is done, we will solve the analysis and we will get the output. Now you can see that the temperature has been generated. You can see the value of the temperature generated in kelvins. If you want, you can also check it in Celsius. Okay. So this is the temperature that is generated inside this block because of the heat generated. Okay. Now once this is done, I am interested into the calculation of the thermal stress induced. Okay. Now the thermal analysis will not give me the stress results. You can see over here. For which now we will exit from the thermal analysis mechanical window, and now we have to add the static structural analysis system to the solution of the steady state thermal analysis. So just drop it over here. You will see that all the data is getting shared, and we just have to enter into the setup now. Once you come to the static structural analysis system, now the data you can see in static structural node, you can see there is one imported load from the above analysis. So it is an imported body temperature which has been imported from here. And now in solutions over here, we can add the total deformation and the stresses that we are interested into, and we will solve the analysis. So now you can see over here, this is the stress value that we have generated. So the stress value is 3.0388 e raised to 9 Pascal. If I want it into megapascal, this is the answer. You can see the animation. Similarly, I can also check the deformation value. So the total deformation that we are getting is 1.0073 millimeters. Okay. If you want, you can use the section tool and see the results internally also. Okay. This is again a post-processing tool which we can use if you are interested into the internal results also. Okay. So this is how you will see your answers. You can see the vector plot for the total deformation also. Okay. So this is how the thermal stresses can be calculated in Ansys Workbench. In this case, we have used two different systems. We have added the static structural analysis system and dropped it on the solution of the steady state thermal system. Okay. So this is how we will perform thermal stress analysis.